Hello and welcome to MAKElog number 16. It has been more than a year now since my last video, so I would like to give you a quick update before I start talking about the GeigerLogger. I've been tinkering around with these small Windows 10 PCs. I've built stainless steel frames to hold the PC part and the touchscreen part together. These PCs are connected to the sensor units to form a bus system. These units use multiple sensors and are connected to each other via CAN bus, so I can read out all the sensors from one single point. Furthermore, my LG G4 broke down because of a boot loop error, and LG didn't want to repair it, and the seller in Hong Kong didn't want to repair it, and so it was quite a hassle to get me a device for video recording again. I was tinkering around with some e-ink displays, and I had my first hands on an ESP8266 microcontroller that I have never used before, and which is the basis for the project which this video is about, a Geiger counter based on this microcontroller. In the Geiger counter I'm using the battery from my LG G4, so this is basically a $600 battery for me because the phone isn't working anymore. Let's switch it on and see what it does. I have an SD card here, where all the data from the Geiger tube, from the GPS receiver, and from the pressure, temperature and humidity sensor are stored. Let's have a look at the display. On the left is a graph which runs from right to left and shows all the counts detected by the Geiger tube. The maximum now is 0 and the minimum is also 0. Here at the right we have the counts per second and the counts per minute. From the counts per minute the microsieverts per hour are calculated. The Geiger counter now records log file number 179 to the SD card. The temperature is 29 degrees Celsius and the humidity is 90%. It's 90% because my hand is here at the sensor and I'm always getting sweaty hands when I'm recording videos for you. Just joking. 1026 hectopascal is the pressure and the battery level is at 97%. This blank area, the display is filled with GPS related data and when a GPS signal is received. Simultaneously, the CSV file is renamed to the actual date and time, and a new file, a gpx-file, is generated, which contains all the data the ESP has access to. Now I would like to show you what I was using the Geiger counter for so far. For example, I took it on some aerodrome circuits in a small plane, and you can see the reading of the display after the flights here. As said before, the GeigerLogger generates a GPX file which I can directly upload to, for example here we see the result from gpsvisualizer.com, and I have encoded the hectopascal pressure reading as color. The next map shows the same track, but here I have used the counts per second as the color scale. As seen from here, I was flying the aerodrome circuit counterclockwise. It might seem there is a higher intensity of ionizing radiation in the western and southern part of the aerodrome circuit, but in fact the airplane speed in the base leg and the final approach is much slower than in the other part of the aerodrome circuit. In this track I have chosen the counts per minute as the color scale. It smoothes out the discrete representation of counts per second. I would need many more measurements for good statistics to prove that the higher intensity of ionizing radiation here is caused by a shut-down nuclear power plant nearby. Besides other flights and other tracks, I did more with the data. Here I have plotted the pressure against the altitude. The pressure value is provided by the pressure sensor, while the altitude is provided by the GPS. As you can see, these two values are in a linear relationship. Furthermore, I'm using the GeigerLogger's generated CSV files for plotting graphs, for example as seen here from some flights. I don't like plotting in Excel, but unfortunately my MATLAB license expired, so I'm using Excel instead. One day I was conducting a battery endurance test. This is simply done by switching the GeigerLogger on, and after the battery runs out I can check at the log file how long it was running. It was running for several hours on my desk. Then I needed to cook something and took it to my kitchen. In my kitchen, I placed the GeigerLogger on my ceramic sink and left it there for some hours. After cooking and eating, I came back to the kitchen and had a look at the GeigerLogger's display. It seemed as if the counts per minute displayed were higher in the sink than on the table. So I conducted a new experiment. I placed the GeigerLogger in the sink and let it run for several hours. The two graphs shown represent the results. Both graphs have the time on the horizontal axis in seconds. The upper graph's vertical axis is in counts per minute, whereas the lower graph's vertical axis is in microsieverts per hour. You can see in the lower graph that the average reading of the microsieverts per hour is 0.23 microsieverts per hour when the GeigerLogger is placed in the sink. Of course, I have repeated the measurements by placing the GeigerLogger simply on my desk and let it run for several hours. The upper graph shows the counts per minute against time and the lower graph shows the microsieverts per hour against time. As you can see, I have measured an average of 0.15 microsieverts per hour when the GeigerLogger is placed on my desk. Let us now compare the results. I have repeated these measurements and they all show similar results. I heard that scientists used strontium ratios to characterize Chinese stoneware. Also carbon might be a factor, but this is all just a guess. Since owning even smaller radioactive test sources is illegal in Germany, I was happy to have a method here to reproduce higher readings on the GeigerLogger simply by putting it into the sink. But this wasn't enough for me. But before we start our experiment, I would like to show you the insides of the GeigerLogger. You need to know that the Geiger tube is oriented like this at this end of the plastic casing. The Geiger tube has one alpha window on this side and the contacts to this side. On both of these sides, the ionizing radiation doesn't need to pass the steel casing of the Geiger tube. So we will get a higher reading of counts per second if the ionizing radiation strikes the tube from the sides. I went to a place where I could put the GeigerLogger in front of an X-ray tube. The X-ray tube was running at 60 kV at 2.5 microamps. The X-ray tube is placed behind the hole at the bottom. I'm now pushing the GeigerLogger slowly into the beam of the X-ray tube. The cross-sectional area of the X-ray beam is approximately 1 square millimeter. In the configuration right now, the X-ray beam strikes the steel casing of the Geiger tube, which causes attenuation. The graph showing the microsieverts per hour is derived by the counts per minute, and the counts per minute are the integrated counts per second. When I turn the GeigerLogger to the side, the X-ray beam directly enters through the alpha window, which causes a massive increase in detected counts per second. After 1 minute of data acquisition, the GeigerLogger's horizontal axis switches from seconds to minutes. This is why you see the white square. I have repeated this experiment several times and here I'm going to show you another one. Again, the top graph shows the counts per second against time and the bottom graph shows the microsieverts per hour against time. I am happy to see that the whole system consisting of the Geiger tube, the circuit and the interrupt routine is running quick enough to detect such high levels of radiation that you won't find in nature. What you have seen until now is the GeigerLogger running from battery, which activates the mobile mode. Another mode, the Wi-Fi mode, is activated if you plug in a USB cable. Now I'm going to explain how the mobile mode works. I'm going to simplify the circuits into 4 parts. One is the GeigerLogger. The GeigerLogger circuit consists of the microcontroller, the Geiger tube, the SD card reader and so on. The second is the USB port right here, which isn't used in the mobile mode. But the GeigerLogger is connected to the USB via a switch. In this configuration, the switch is in the upper position. In the upper position, the GeigerLogger circuit is powered by a DC-DC converter. The battery side of the DC-DC converter is connected via the right switch to a lithium-ion battery. In this configuration, the right switch is in the upper position to connect the battery to the DC-DC converter. If we put the left switch into the upper position, we connect the DC-DC converter to the GeigerLogger to power the GeigerLogger. The ESP8266 only allows a voltage level up to 1 volt at its ADC. So I have built a voltage divider simply consisting of 2 resistors shown here. The voltage divider allows me to measure the battery voltage picked up at the DC-DC converter input. Let's have a look at the Wi-Fi scenario now. Again, the GeigerLogger circuit is represented here on the left. But this time the left switch is in the lower position, so the GeigerLogger is powered directly via USB. The DC-DC converter is connected to the USB port permanently. For the Wi-Fi mode I put the right switch into the lower position to prevent the battery from charging. But if I want to, I can connect the battery to the DC-DC converter to let it charge. Let's test the Wi-Fi mode now and plug in a USB cable. Right now the battery is disconnected and the ADC of the microcontroller would measure 0 volts, so it will start in Wi-Fi mode. In Wi-Fi mode the radiation measurement is integrated over 1 minute and sent together with the other measurements from the pressure, temperature and humidity sensor and the battery level to an external service, which is ThingSpeak in this case. I took the original Redmond software as the basis for this GeigerLogger, which allows me to configure the services, the Wi-Fi password and many other settings. By pushing this button on startup, the ESP works as an access point which provides a web server where I can change all these settings. The other button activates the beeper for each count. Let's have a look how I have built the GeigerLogger. I have started with a plastic casing which is big enough for the main PCB and the battery. I have added a slit for the SD card. I had no mill when I made the slit for the USB port, as you can see. The micro USB port belongs to the DC-DC converter and is the voltage input. I have cut the PCB to fit into the case and use minimal space. Next to the DC-DC converter I have placed the SD card unit. I have removed the pins to make it as flat as possible. I simply glued these 2 PCBs to the case. As a battery I have used the battery from the boot looping LG G4. In the left of the case there is enough room for the Geiger tube. The ionizing radiation should only strike the Geiger tube and not the circuits. This is how it all looked during development. You can see the Geiger tube, a small battery for testing and the real battery, an OLED display and a GPS receiver, which is from an old Holux GPS Slim, which I don't need anymore. Especially for the GeigerLogger I've bought a small milling table, which I was using here for the first time. Here you can see that the hole for the OLED display is now finished. To keep the attenuation by the plastic casing of the GPS signal as low as possible, I have removed material by milling. Here you can see how the GPS receiver fits inside the case, and also I'm adding the OLED here for demonstration. I realized that the GPS receiver needs around 200 mAh, which is quite a lot, and I can't deactivate the onboard Bluetooth module. Then I was looking for components that need much power. I didn't want to touch the high voltage circuit just to check it for temperature. So I took a thermal camera to have a look for power consuming components. I could only identify those components I have already expected. That's the GPS receiver, the microcontroller and the DC-DC converter. But let's have another look here. Because infrared is just a longer wavelength than visible light. So it can also be reflected, which I'm demonstrating here. You can see that the metal surface reflects the photons from the direction it's pointed to, which is the similar effect if you would take a picture of a mirror. You can't take a picture of the mirror because you only see the reflection and not the mirror itself. The solution to this is to paint the surface you want to measure in black. If it would be white, you might measure stray radiation. That's it for this video. I hope you have enjoyed it and have learned something. See you soon!